Local check 1, 2, 3. Okay, welcome Cisco cohort 2 to this last synchronous session for the lecture on modules 14 through 17, where we'll be covering the transport application layers, the upper layers of the TCP/IP model. And we'll take a little bit of a look at security and building a small network. Wednesday will be our last in-person lab at SBUS 1125 at the South Campus. We'll go over lab 229. And of course, I'll tape that and post it as well for those asynchronous viewers that we'll be looking at later. This final exam week will start this Wednesday at 9 a.m. And the final exam, you don't get a whole week to take the final. I mean, you only get about an hour and 30 minutes, 45 minutes to take the final once you start it. But you can take it at any time during that window between 9 a.m. of this Wednesday and 9 a.m. of the Wednesday after that. Just a reminder that Cisco does have a business rule or a business requirement that before you go to netacad.com and take the chapter, take the final exam, it's the same place you take the chapter exams on Netacad. You have to take that course feedback form, which is an anonymous student satisfaction survey. So you see a message on there. If you haven't taken that, under the final exam, it'll say it's not available. So you take the course feedback form first, and that takes 5 or 10 minutes. So next week, being final exam week, there will be no lecture on Monday. This is the last chapters we're covering today for the finishing up the course. And then a week from this Wednesday, there will be no lab because the class ends at 9 a.m. that day. Okay, we just got some attendance here. I got to record. Okay, I'm gonna stop sharing this, and I'll start sharing the 1, 2, 3, 4, 5. Start sharing the first chapter we're gonna look at today. Okay, a lot of stuff going on in the transport layer, a lot of important jobs that are taking place at the transport layer, such as positive acknowledgement and retransmission, which means that any lost data is retransmitted, so we get the whole chunk of data. And also the TCP has got a function that it can keep track of separate conversations that are going on the PC. So you could run a web browser, 2 web browsers going to 2 separate websites, and the proper data will end up in the right browser window and will get mixed up. So let's see now. I'm sharing this, and I should be able to go like this. Okay, so transport layer gives us communication between applications running on different host machines. So the computer itself has an IP address, but the computer, desktop Windows machine can run more than one process at the same time. Or think of like a web server at Cisco or Microsoft or Amazon.com. That one web server has many different people connected to it at the same time. It has to keep all those different communications separate from each other. So it can do this using this concept of port numbers. So here are a lot of things that it does. It tracks individual conversations. So in this case of this graphic on the right here, we've got a single PC that's running. He's doing streaming audio or streaming video. He's doing a video session. He's running multiple web pages. He's running an instant messaging service. He's running email. So this allows us, this one single computer, which only has one physical MAC address and one physical IP address, one logical IP address, to run several different applications at the same time. And we're going to add this layer 4 identification information by adding unique port numbers. We're going to keep these conversations separate from each other. So individual conversations are tracked. The transport layer also takes upper layer data and he separates it into what we call the protocol data unit at the transport layer is called a segment. So we had bits at the physical layer. We have data link layer frames like Ethernet frames at the data link layer. We have network packets, IP packets, for example, at the network layer. And then the transport layer, we're at the individual segments. And when we get into the upper layer, the application layer is just a solid stream of data. The application layer hands that down to the transport layer. And the transport layer, one of the things he does is chop that up into small, manageable size segments, which eventually will be encapsulated in the network packet. And that packet will be encapsulated in a Ethernet frame. And the Ethernet frame will be turned into bits, and the electricity of the ones and zeros will be shot up over the wire. So the transport layer does add some header information, including such things as port numbers. he uses these port numbers to manage all these different multiple conversations that are going on. And let's see, how many port numbers can we have? It's a 16-bit value. So that means we can have over 65,000 different unique values. So it's no problem. With Windows, Microsoft Windows, that's no problem. If you try to run more than 5 things on Microsoft Windows, hey, it's going to crash and you're going to have to reboot. So 65,000 is essentially unlimited numbers for workstations. And TCP will use, transport layer will use segmentation and multiplexing. So different conversations can go on the same network. At the physical layer, I don't know what you have one MAC address, and at the network layer you have one IP address. But at the transport layer, we can have port 80 for your web, port 25 for your email, and we can keep all these conversations separate from each other. Now, IP itself doesn't tell how the delivery of the packet takes place. So transport layer protocols, in other words, that IP and the internet layer, the network access layer on down, it's essentially connectionless. They don't have any ability to manage that. But at the transport layer, we're going to set up a communication session between what that individual application program you're running on a PC, like maybe a web browser, and that one web server host that you're talking to. And you can run multiple tabs, or you can run 2 different web browsers and have 2 different conversations taking place at the same time. So the 2 big protocols we're talking about with at the transport layer is Transmission Control Protocol, which is the one we mostly use because it has all the features. It keeps accurate data, retransmission of data if anything is lost. And then a more simplified version called User Datagram Protocol for quick and dirty stuff like, a DNS request. Or if you're doing streaming audio and streaming video where TCP is just too much overhead and you can tolerate slight loss of data, we'll use that. We'll use UDP for that. So Transmission Control Protocol is reliability, flow control. It's going to take the upper layer data from the application data and it's going to chop it up into smaller size segments and it's going to number them. It's going to put sequence of acknowledgement numbers on them. It's going to transmit some segments to a receiving host, and the receiving host will acknowledge back to the transmitting host that he received the data okay. If he fails to acknowledge that he received the data, then the transmitting host will attempt to resend the data. Any data that happens to be received out of order, that's okay. TCP will look at the sequence numbers and he'll be able to put the data back in the correct order. And there's also a feature called flow control, which means that, well, say it's Prime Day and the Amazon servers are getting overloaded with millions of people coming in to buy the latest big deal on a tablet. Well, the servers have the ability to send back a message to the transmitting machines, the millions of people trying to come in and buy their products, that he's really busy right now and he's going to accept your data, but at a slower rate than you can send it to him. So it has the ability to sort of choke back the rate of data so that it can be at a data rate that's understandable, that the receiving host is very busy, that he can handle right now. So a lot of things taking place. User Datagram Protocol is if we want very little overhead in data checking, and maybe it's something like streaming audio, streaming video with so much data that I can't check and do positive acknowledgement and retransmission for each little bit of it. And I'm able to tolerate slight losses in data. So UDP is used for things like streaming audio, streaming video, voice over IP telephones. Used for things like a quick and dirty request to a name server. Quick Mr. DNS server, look up the exact 30-bit IP address for netacad.com because I want to log into that with my browser. Best effort delivery only, not positive acknowledgement and retransmission like TCP would do. So things like if we want fast, low overhead, I don't need acknowledgements. I don't have to resend lost data. I'm just going to deliver the data as it arrives. And he gives the example here in the graphic of streaming audio like voice over IP telephones or DNS resolution. But for many applications, we want absolutely perfect data. If I'm sending a Service Pack 1 update for the Windows 10 operating system, I can't flip any of those bits in there at all. Otherwise, it might erase my hard drive or cause my computer to catch on fire. So TCP, if we need absolute reliability, we're going to acknowledge each bit of data as is being sent, and any data that's not acknowledged will simply be retransmitted. The data will be delivered in a sequenced order, and if it happens to be received out of order, he can use the sequence numbers in the headers of those TCP segments to put everything back in the proper order. So usually it's important that all the data is proper. Quick and dirty stuff like DNS requests or streaming audio and video, we can tolerate small errors in that. We'll use UDP for that because it's very low overhead. TCP is much more overhead. So TCP establishes a session. We're going to look at this thing called sync ACK, where the sending and receiving workstations make sure that they're able to start talking to each other. It ensures reliable delivery, because if anything is not acknowledged, it will be simply retransmitted. It will provide same order delivery, because if something is sent and it takes multiple paths and it doesn't be received by the receiving host device in the same order it was transmitted, the receiving host can simply, computers love to sort numbers. They're good at that. So if data is received, he simply sorts those incoming segments back into the proper order that they were transmitted. And we get an exact Xerox copy or duplicate of the original data, the ones and zeros. And this flow control feature, which if a network host runs out of resources like Amazon on Prime Day, he can request that sending applications slow down. Here we see a header of a TCP segment. And we have our 16-bit source port and our 16-bit destination port. Then we have two 32-bit values. These are our sequence and acknowledgement numbers that when we're transmitting a large amount of data that had to be chopped up into individual segments, the segments will be numbered. And they'll be numbered so that if they're received out of order, they can be put back in the right order. And there are some other bits for things like establishing sessions and sending error messages and things of that nature. So source port, 16-bit field for the source number. It's a 16-bit field, 65,535 values. So for example, port 80 is the well-known source port for web. Port 25 is a well-known source port for email. Sequence and acknowledgement numbers to put things back in the right order. And we have some control bits to do things like set up the communication. So any application that wants to divide the data stream into segments and give us reliability, positive acknowledgement and retransmission, controlling the data flow, putting segments back that might be received out of order, TCP is the job for doing this. And in this graphic, we have TCP at the transport layer. He's handing his information down to IP. He gets something from the network. He sends it up to looking at the port numbers. TCP will look at, oh, that's port 80. Send it to the web browser. That's port 20 and 21. Send it to the FTP file copy program. At Secure Shell, send it to the proper port number for Secure Shell. Simple Mail Transfer Protocol, port 25, send it to that proper port. So I can have multiple applications running on an operating system like Windows, which allows you to do many different programs at the same time. Not too many, 5 or 10, and then it crashes. But you can run multiple programs at the same time. Now UDP is no positive acknowledgement retransmission. It's fast and quick and doesn't have a lot of overhead. Any segment that is lost is not resent. There is no initial session establishment with the sync ACK. So the UDP header is much simpler. It merely has the source and destination ports and the application layer data and a little bit of checksum to check for very primitive errors. So this is great for things that don't need a lot of overhead, like streaming audio or streaming video. Voice over IP Cisco telephones use this feature. Or maybe you're making a quick and dirty DNS request to the name server at your ISP to look up the actual 32-bit IP address or the actual 128-bit IP version 6 address of a device you're trying to connect to. So live video, multimedia applications, they can have some data loss, but they're very sensitive to latency. They don't need any delays. So voice over IP telephones need like dial-up modem, screeching cats modem bandwidth. They don't need a lot of bandwidth, but they're very sensitive to latency. Anything more than a 1/10 of a second latency, and the telephone conversation is going to sound like a cheap Walmart prepaid cell phone. So a simple and request and reply application like, quick Mr. DNS server, give me your, what's the IP version 4 address for Cisco Networking Academy? Or quick Mr. DHCP server, I request an IP address. UDP is used for things like this. Now there are some applications that handle their own reliability. For example, trivial file transfer protocol is commonly used. We'll see this in a course we take in the later part of the fall. We use TFTP commonly with network devices to load and save configuration files like the startup configuration file or the iOS file. So TFTP has its own error handling for this. Let's look at this concept of port numbers. There's a 16-bit port, just as your web browser application on your desktop PC and the web server and a web rack mount somewhere in a data center, they both have their own unique IP addresses at layer 3. They both have their unique MAC addresses at layer 2. Well, at layer 4, we have our own unique port numbers. So the port numbers used to separate your request from some other requests when you log into Networking Academy. You know, you get your chapter, you get your test, you don't get it mixed up with some other students. So the source port, when you're a workstation, your source port will be some random number above 1,000 on a Windows machine. The destination port will be port 80 on that web server. Port 80 is a well-known port for web services. Port 25 on that email server. And this combination of your layer 3 IP address and your layer 4 transport port number makes your session completely unique and identifiable. So the source and destination ports, they're in the segment and they're encapsulated within the packet. So in the packet, we're going to have the MAC address at layer 2, we're going to have the IP addresses at layer 3, and we'll have the port numbers at the transport layer. Sometimes called a socket, this combination of IP address and destination address. So this way, one device, like a multi-user operating system or a multitasking operating system like Windows or Unix or Mac OS X, can run several different processes at the same time and allow them to all have simultaneous connections over the network. Here is the lowdown on these ports. It's a 16-bit value, so any number between 0 and 65,535. The numbers below about 1,000 are reserved for servers. You cannot source the data on a port number below 1,000 because you are not a server, you're a workstation. Now, if you're a server in a rack, yeah, you're going to source the web server traffic on port 80. If you're email, you're going to source the traffic on port 25 for email stuff, for transmitting email. So numbers below 1,023 are reserved for server applications. Ports above that are pretty much wide open for workstation machines like Windows or Unix or Mac OS workstations to use as their source port numbers. So these are just picked sort of at random by Windows Workstation, and they'll automatically pick different values. If you're running 5 processes, they'll automatically pick, say, 1100, 1101, 1102. They'll pick unique numbers so they don't conflict with each other. Sometimes these are called ephemeral ports because they're just used sort of temporarily. Here are some well-known port numbers. So file transfer protocol uses port 20 and 21, Secure Shell port 22, Telnet port 23. For transmitting email, port 25. DNS uses port 53. Dynamic host configuration protocol uses port 67 and 68 to request and receive data. Here are some well-known ports. There is a command you can type on your Windows machine, also on Unix machines too, Linux machines, or Mac OS X. You can type the command netstat, and it'll show you, look at all those sockets that are listed there. We have the IP address of 192.168.1.124, colon 3126, 3158. That combination of a layer 3 IP address and a layer 4 port address forms a unique socket for that particular communication that's taking place. So in this case, the user is running one browser that's going to the Microsoft network. Let me show you a pencil here. He's running one web browser, and is running another web browser that's going to the Cisco website. And you can do that on Windows. You can run multiple tabs on your browser or run 2 browsers. Every application process is going to use some unique port number so it doesn't conflict with other processes that are running on that same device. Can't have 2 services assigned to the same port number. So if you're a workstation, you're going to use this ephemeral port concept and just randomly pick. Windows machines usually pick a number above 1,024, and the next one will be 1,025, and the third one will be 1,026. And those increment this number up and up. Server machines, however, have to listen for a specified port. If you're a web server, Here's his web server right here. He's configured to be a web server and a mail server. He's listening on port 80 for incoming requests for the home page. The mail server is listening to port 25 for incoming requests to transmit some email. The source ports on the individual machines are these high numbers that are above 1,000. Now it's supposed to be above, 50,000 or whatever, but Windows machines, they don't pay attention to the rules. They typically use something after slightly above 1,000. So before any data is being transmitted, the two workstations have to agree that they're willing and able to talk to each other. The receiving workstation sends a message and he sets the sync bit in the TCP header, and workstation B receives it. And workstation B is ready to respond to it. It's not like the servers at Prime Day that are overwhelmed and they're crashed. So he'll send back a sync ACK. Workstation A will receive the sync ACK and he'll send back the sync ACK. This is called the three-way handshake, the TCP three-way handshake. Now we can start actually sending the data back and forth. We have established that where A and B are able to talk to each other. And we've also set up our initial sequence and acknowledgement numbers so that no matter how much data we need to send, the sequence and acknowledgement numbers will make sure it can be put back in the right order when it's received at the receiving workstation. Now, when I finish sending my data, we haven't looked at the actual sending of the data yet, but when the data session is over, we use sync ACK to set up the session. Now when we're ready to hang up the session, to terminate the session, we're going to send fin ACK, and that means the connection is over. So for example, when you log onto when you go to a web server, a web page, he sends you back his home page and then he disconnects the session. Kind of like the telephone company doesn't have unlimited dial tone. If you take your phone off the hook, you're going to get dial tone for about 15 seconds, and then you're going to get ooh, you get those little noises. He doesn't have any dial tone to give you. He only has a limited amount of dial tone for the 1 or 2% of his customers that are on the phone at any particular time. So web servers only have a limited amount of CPU power to handle this connection. They're not going to wait around for 5 minutes looping around for you to click the next link. They're going to send you the home page and they're going to disconnect you. Now, when you click on the first link on the home page, you'll do a new sync ACK. You'll get that elements and then fin ACK, you'll tear it down. So the three-way handshake makes sure that the two devices, the source and destination devices, are present and can hear each other. They've verified that the destination device, maybe a web server, has an active service like an HTTP web server listening on port 80 and is accepting requests. And it tells the web server what this ephemeral made-up number on the client workstations are not allowed to use numbers below 1,000. Only servers can use those to source information. And this informs the destination device, that web server, that, oh, I'm a Windows workstation and I'm listening on port number 11,000. And I want you to send me back to that port number. Here are the 6 flags which are in the control bits. We see the sync and the ACK. We see the reset to reset the connection. We see the fin for the fin ACK when we tear it down, finished. We see urgent, sounds like a Foreigner song, urgent. These 6 bits are never set at the same time. Now, we're going to talk about a little bit of security later on today, but some hackers, well, that's not malicious intruders. We're not supposed to say hacker anymore. Malicious intruders, threat actors, have figured out that Windows computers don't have very good code in them. And if we light up all 6 of these bits at the same time, they call this a Christmas tree attack. You can crash Windows workstations and do buffer overflows and take control of the device like you would the administrator. Normally, only 1 or 2 of these are on at the same time. Okay, reliability and flow control. TCP has a feature that, in this case, the transmitting workstation sent 1, 2, 3, 4, 5, 6 segments to the receiving workstation, but they were not received in order. They were received sort of out of order. But the sorting code will put them back in the correct order, so we have the original configuration of the original data will match when they're put back in order. So if it's a text file, the pages will be in the right order. If it's a executable file, like a COM or exe file, the bits will be in the proper order and they'll work properly. Now let's say that something fails. Here's segment workstation A is talking to workstation B, and he sends 2 segments to it, and segment 3 and 4 are never received because there was a collision or something went wrong. They were never received. Segments 5 through 10 were received okay. So what should workstation B say back to workstation A to tell them that, well, I got segment 1 and 2 okay, but I never got 3, I never got 4. So he sends back the message saying acknowledge 3. This is code for I acknowledge that I got 1 and 2, okay, and I need 3 next. I never got 3. So workstation A will simply retransmit 3, 4, 5, 6, 7, 8, 9, 10. And then this time they were received properly. And the receiving workstation will now say acknowledge 11, which means I got everything 1 through 10. Okay, I expect to receive your segment number 11 next. So in this way, anything that's lost due to whatever reason whatsoever, for whatever reason that we cannot receive those segments, the receiving workstation can tell the transmitting workstation to simply resend those. And eventually we're going to just keep on doing this until we get all the segments for that chunk of data. So selective acknowledgement is a newer feature that allows them to only retransmit the individual ones that were lost, not everything again. So this cleans up the reduces the amount of data that needs to be retransmitted. Now look at this flow control feature. Flow control is how much data am I willing to accept from you? So Amazon's got their Prime Day going, all their servers are really, really busy. So they need to be able to, the Amazon server racks need to be able to send a message back to the millions of people that are trying to log on and you know, get the first million tablets before they first run out, to tell each of these million guys that are trying to log on right now, I'm going to get your connection, but you need to send to me more slowly. I'm going to reduce the size of this window of data that instead of taking 10,000 chunks of data from you at one time, maybe I'll reduce it to 1,000 chunks. So in that way, a workstation, a server, and a server rack can tell the thousands and millions of people trying to connect to them to slow down. And I'm going to get to you, but we're going to have to dribble the data just a little bit. So this maximum segment size is what the receiving workstation says. This is the maximum amount that I can receive at any one time. So a common size might be 1,460 bytes. If we take the 1,460 bytes and we put it in an Ethernet IP packet, Ethernet frame, Ethernet frames are 1,500 characters by default. So that'll just fit properly. And congestion, if a congestion occurs, TCP has some congestion methods to reduce congestion. Then let's look at UDP. No sync, sync, sync. No FINAC, no acknowledgement of data whatsoever. Good for quick and dirty stuff like a DNS request or a DHCP request. Or streaming audio or streaming video, where if we did the acknowledgements, positive acknowledgements on each and every part of a video frame, the video would be unworkable. You know, like when you get that circling, scrolling thing on YouTube, it's too slow, it would never work. We can't acknowledge those stuff. So we're going to tolerate the loss of small amounts of data. In a streaming audio or video, that's a crummy MP3 file anyway. You're not going to notice any difference. So no connection is sent before sending the data. So the data is taken in the order that it was received. It's up to the application layer to put it back in order if he needs to do that, like with TFTP. So user datagram protocol, for example, a DNS request is port 53. The client sends a request to port 53 to the server to look up a certain domain name and return the IP address. The Radius client, we haven't talked about that. Radius is a mechanism that if we have 300 routers, we don't have to set the passwords on all of them individually. We can use a Radius. It's kind of like a Microsoft Active Directory domain controller where you store the central password on one computer. You don't have to put it on 5,000 computers. So the server is talking to the Radius client to make sure that it's using the right name and password, and then the server is talking back to you to give you a DNS request. And these are all unique port numbers and unique IP addresses, so they don't mix up the data back and forth with each other. I think that's it for this one. And now we're going to go to module 15. Can I say share now? There we go. Now we're up to the application layer. So at the dreaded, feared, and hated OSI 7 layer reference model, we've got these application, presentation, and session. In the TCP IP model, they're all rolled together into application layer protocols. So hypertext transfer protocol for sending web pages, file transfer protocol for downloading support files, TFTP for backing up and restoring startup configuration files and iOS files to Cisco routers and switches, IMAP for picking up email, DNS for sending my quick Mr. DNS server. What's the IP address for Microsoft.com? I need to go there, TechNet. The presentation and session layer, there's very little emphasis on this in the CCNA objectives. But the presentation layer, it briefly is responsible for in what format is the data presented. So for example, a music file might be MP3. A picture file might be a JPG. A movie file, Apple movie file might be MOV. So any formatting of data is considered presentation layer. Also, if we're compressing any data in any way, like with WinZip, that's a presentation layer topic. And if I'm doing any encryption and decryption of data, that's all presentation layer stuff. The session layer is responsible for opening and closing a session. So when you come into the in-person lab and you log in the Microsoft Active Directory domain services with your name and password, you're granted a session onto the Microsoft network, and you can, print to the printer and use stuff on your computer. Now let's look at application layer protocols. Now this is very much a CCNA objective. So at the application layer, we have several different protocols, about a dozen that we're really interested in for purpose of CCNA. The DNS service is what allows us to type in a domain name like Cisco.com, and it's translated into an IP address, because I can't put the word Cisco.com in the package. I've got to put a 32-bit IP address. Or if we're using IP version 6, I have to put an IP version 6 128-bit address. If we're using DHCP is pretty much universally used today, both in home networks and commercial networks, to assign IP addresses dynamically to workstations. So we, as network technicians and engineers, don't have the extra added job and burden of having to run around and statically configure stuff. And web traffic, port 80 or port 8080 for unencrypted and encrypted web traffic. Now Microsoft, let's talk about the dreaded, feared, hated Microsoft. We have some Microsoft courses here. You should learn about a little bit of Microsoft. In industry, you probably expect to know a little bit about Microsoft and Linux and security and things of that, as well as being network technicians and engineers. In the client server model, we have a dedicated server machine somewhere in a server closet. And then we have a client that requests the data. So clients request services and servers fulfill these requests for services. And Microsoft says that if you have more than about 10 or 12 people in your business, you should use this model. You should use the client server model instead of peer-to-peer, because it's more scalable. Now this means you're going to have dedicated hardware network servers, like a Microsoft rack mount server that runs the Microsoft Active Directory domain services and file and print services on your company. You're probably going to have an employee or more than one employee to install and manage and configure these devices and reset people's passwords. If you're a small company and you only have, 10 or 12 people, you probably don't have a dedicated file server machine. You probably don't have a dedicated network administrator. So with Microsoft Windows, this peer machine number 2 has a printer connected to them, and the person that's sitting at the peer 1 workstation needs to be able to print. Of course, they're all plugged into a Cisco switch or some other switch. Well, you can right-click on your printer in Microsoft Windows and share the printer to the rest of the people in your small company. You can set a password if you want to. The person seated at desk peer 1, they might right-click and share accounts receivable file so that people can do it, and there might be another password for this. This is okay for 10 or 12 people in the company, but the model breaks down when you get much above that because there's too many passwords to remember. You'll find if you're ever in a help desk environment that most people find it especially hard to remember just one password, not to mention 3 or 4. So when you work at these type of companies, you can always tell because you go to the coffee break room and there's everybody's passwords for everybody's on a sticky note on the coffee machine, not high security. A peer-to-peer application then allows the device to be both a client and a server. So I could right-click on my printer and share it, and I'm serving the printer to my other people in my small company, and I can run a client machine at the same time, or a client application program at the same time, like an instant messaging program or a web server program. So common peer-to-peer applications. Let's see, what was the Napster? You guys remember Napster? It was this method of sharing music files without having to pay for them. And all the MP3 files would be stored on a server in Russia or something like this. And you could just go and download them. And the music companies got real mad and kind of shut Napster down. There was a central server in Norway or something, and they went and just closed it down. Well, peer-to-peer file transfer networks like, BitTorrent is a very popular one these days. With the BitTorrent, there's no centralized server to shut down. So let's see, let me think of, have you ever heard of thepiratebay.org? It's a place you can go to get movies and music and commercial software without having to pay for it. But they don't store the files there. The files are stored on a bunch of individual users' machines at a bunch of different ISPs. So when you download a BitTorrent file, you get a little bit from one user and a little bit from another user, and there's not one central server that the music industry people can hire a big lawyer and come down and steal their server and shut it down. And it's a much more efficient way of transmitting data too. Now there are plenty of legitimate uses for BitTorrent. If you're going to get Linux, you can go to a Linux site like Ubuntu, and you can download it via BitTorrent instead of having to put a big burden on their download service. So it has valid legitimate uses. Okay, Hypertext Transfer Protocol, HTTP, and Hypertext Markup Language, HTML. I'm going to type in to my web browser. I'm going to type in http://www.cisco.com/index.html. That's a completely specified uniform resource locator, and I'll be able to see their homepage. The browser, after you type that into your web browser software, the first thing that's happened is the browser needs to say, well, I can't put cisco.com in that packet. I got to put that 32-bit IP address. So he sends a request to the DNS server and says, please tell me the exact IP address of cisco.com so I can make a packet and send it to him. Then the packet with that numeric data is sent to the web server, and the web server sends him back his index.html file. That's the default homepage that you see when you go to any particular web page. And then the web server sends back that response to the client. He sends back the code, and the client gets the pretty pictures and graphical layout that the web designer for that particular web page intended for users to see, regardless of what kind of platform they're on, whether they're on Windows or Macintosh or Linux. They'll see the same thing, mostly the same. HTTP is normal unencrypted traffic. It's not secure. There is an alternative. He talks about the get, post, and put commands. When you get the home page, that's a get command. When you want to post a form, like some companies have, say, fill out this form on my page and send us a request for information. Or if I want to upload the data to that, I've used put to put data on it. But HTTP itself is not secure. So there's an alternative called HTTP Secure that encrypts all the data back and forth. And this is what you normally use if you go to your bank webpage and you want to check the transfer money from savings to checking. Or you go to Amazon and you're going to buy something and you need to put in your credit card number. Well, you don't want anybody in the world to run Wireshark and get your credit card number or get your bank account information so they can steal your banking money. So Hypertext Transfer Protocol Secure encrypts this data, and the only people that have the keys encrypt and unencrypted data are you and the bank, or you and Amazon, and no one else can steal something in your credit card. Email is 3 different protocols here. Simple mail transfer protocol is when you click on a traditional email client like Eudora or Microsoft Outlook, and you click the send button. It makes a connection with the email server, and it receives your data and begins to relay it. When you pick up your mail with these typical, I'll call them legacy clients because most people don't use them anymore, use post office protocol, IMAP, to pick up and receive your mail. Now, most people these days are using web-based email like Hotmail or Google Mail or Yahoo Mail, and this reduces the entire function to a web page. So only HTTP and HTML are used between you and when you log in and get your mail. But at Google, they have mail servers and receivers, and at Hotmail, Microsoft's got email servers and receivers, and so forth. So simple mail transfer protocol is used to send mail. I'm going to click on send mail, and if I'm using a traditional client program like Eudora or Microsoft Outlook, it'll use a simple mail transfer protocol to send it to my ISP's mail server, and then it'll relay it onto the recipient. So whenever you send mail, it's simple mail transfer protocol. Whenever you pick up mail, it's POP3 or IMAP. So these simple mail transfer protocol and POP3 and IMAP3 are not commonly used by home users or corporate users anymore. They typically will use a web-based server like Google Mail or Hotmail or something like that. Okay, IP addressing services. We can't expect our users to write down and remember 32-bit binary numbers. Even dotted decimal for IP version 4, that's too much for them. I want to use something an easy to remember name like Cisco.com, Microsoft.com, Netiquette.com. So the DNS protocol is a protocol that I call it the Directory Information Operator of the Internet. It allows us to type in an easy to remember name like Microsoft.com or Cisco.com, and then our desktop computer will automatically make a request from the nearest DNS server. What's the 32-bit IP address for that? Because I need to put that in the packet when I create the packet. So there are some different types of things in the DNS. I can ask for an in-device's IP version 4 address. That's called an A record. I can ask for an authoritative name server, like Google has a name server at 8.8.8.8. The Quad 9 project has a server, a DNS server at 9.9.9.9 that does a pretty good job of filtering out malware. 4A's, Quad A, that's an IP version 6 address. And if you're sending and receiving email using the legacy programs, which most people don't, they use web-based stuff now, it's an MX, a mail exchange record. So DNS uses a uniform message format where he sends a question and gets an answer, and there's an authority record that says I have the authority to give this proper information to you, and we can give additional information. There's a hierarchy of DNS root servers. There's I think about 13 root level servers around the world, and the idea is if there's a flood or a hurricane or a bomb or something that knocks out one particular area, there'll still be other root servers that have the same uniform list of all the web servers in the entire world. So if you click a request for relatively new, let's say you get one of the $7 a month web pages, and you'll go and you'll pay your $7 and they'll set it up for you. And for about an hour or two before this propagates back to the root level servers to the rest of the world, other people might not be able to get to your new web page for an hour or two. And then it eventually be propagated through all the rest of the web DNS servers in the world, and they'll have connectivity to you. So we have top level domains like .com for business, .org for a not-for-profit, .net for networking companies, or top level country domains like .uk for the United Kingdom, .ua for Australia. There's a troubleshooting command that we can use to check our DNS operation on our desktop PC. We can type the NS lookup command and then type in cisco.com, and it'll do a DNS lookup for us and make sure you can test and make sure that your DNS service is working properly. This is the exact same function that takes place when you run a web browser and you type cisco.com. He looks up that number for you and he provides that. So your computer application can create a packet with the proper IP address in it. Okay, Dynamic Host Configuration Protocol came out in the mid-90s, and before that came out, and I was working in networking before then, and we had to statically configure everything. Well, normally we statically configure printers and servers and routers and switches, but we normally don't like to statically configure employees' desktop PCs because they're moving around all the time, and they're Macintosh users. They think they know everything there is to know about computers. They just make up numbers and put them in there, and it messes up the network. So when this came out in 1995 or so, we were able to put DHCP servers in our server departments. And anytime anybody plugged in a laptop or a desktop PC and moved from one office on one floor to another office on another floor, they would automatically get the proper address for that new location they moved to. So this automatically hands out the proper IP address and subnet mask and default gateway and DNS server and so forth. So whenever a workstation boots up, he sends out a broadcast message saying, calling all workstations, calling all host machines. If you're a DHCP server, I don't even know my IP address yet. All I know is my own MAC address. Please send me back what IP address and subnet mask and default gateway and DNS values I should use. Normally, we do statically configure network devices like servers and printers and routers and switches. There's a similar function for IP version 6 that gives most of this information back to the client machines, and we're supposed to be migrating away from legacy IP version 4 and go to IP version 6 in the future because we have so many more network addresses available for us. We don't have to do any network address translation, other band-aid stuff we had to do in the mid-90s when we started running out of IP version 4 addresses. So the DHCP process is called DORA the Explorer. The workstation is going to boot up, the DHCP client machine is going to boot up, and he's going to send out a broadcast message saying, I'm attempting to discover any other DHCP servers on the network. And there may be more than one. Microsoft recommends you have 2 to back each other up. Why? Because Microsoft servers crash all the time. Well, one or more of these DHCP servers will hear your broadcast request, and they'll send you back an offer saying, well, hey, I have an IP address and subnet mask that you can use. Are you interested? The DHCP client will then come back and request that particular one. If there's more than one DHCP server, he'll pick the one he likes. Microsoft computers, for example, tried to use the same one they used last time. Then that server will send back an acknowledgement request, and this closes the sequence. He's given the address to you. He's taken it off his list of available addresses and put it on the list of addresses that have already been allocated, and they shouldn't be duplicated. Now let's look at file sharing services like FTP. FTP allows us to transfer files from a server to a client machine. You can still go to ftp.microsoft.com and download service packs for NT version 4.0 and their other products. And many times when you go to a Microsoft TechNet site, you download something, you'll see FTP:// in your web browser. They've actually shifted to an FTP server to download the file to you. Now, FTP is a kind of a weird bird protocol because he needs 2 ports. He uses port 20 and 21. Port 21 is used for the commands. Port 20 is used to transfer the actual data. Server message block is this is what we use at school. When you log onto your Microsoft Active Directory domain services server that's back at the Trinity River data center, this is what checks your password and makes sure your password is proper. And then they give you authorization to unlock that and use that computer. And server message block is used for shared files and folders and sending something to the printer. It's a long-term connection that lasts until you log off. Okay, now we need to go to, let me see, I need to stop sharing this. And I think I'm going to do this one next. And let's talk a little about network security. So what are the types of threats that can arise when a malicious user, a threat actor, gets into your network? So intruder has somehow gotten access he's gotten somebody to click on a bad link, you know, a phishing link on an email, or somehow gotten into, and maybe wants to be ransomware or something like this. So 4 types of threats: we can steal your information, we can thieve your information, we can make you lose your data, we can perform identity theft or disrupt services. So the ransomware guys, what they do is they encrypt all your data, and they say, we're not going to give you the decryption key unless you give us, you know, 100 bitcoins or something. Well, no, that's too much money. 100 bitcoins is like $1 million now. That's some reasonable ransom. You know, a couple $1,000 or $10,000 for a big company. So vulnerabilities are weaknesses in products. Microsoft Windows has got lots of vulnerabilities. The older the product is and the less up-to-date service pack it is, it'll have more weaknesses. There may be some weakness in the TCP/IP protocols themselves. The network equipment or the operating system might have vulnerabilities. So this might allow a known vulnerability to be breached using a buffer overflow or some other policy, and now I'm a bad guy and I've got supervisor level, administrator level access to your machine, and I can, you know, encrypt all the files and do the ransomware or steal data, things of that nature. Okay, there's technical security and there's physical security. Technical security is like a password. Technical security is like encrypting the data. Physical security is having a lock on the door to the server closet, having IP surveillance cameras to make sure that only the right people are in the right area. Hardware threats, damage to servers, environmental threats. If the temperature gets too hot, then the servers will start shutting down. Electrical threats. We can maybe use a UPS on our server so that if the power gets lost, the server doesn't crash. Windows is very nasty if you just turn the power off. It's got 120 open files and now they're all corrupted. There could be maintenance threats. Now let's look at some ways of attacking on our network. What are these? The word mal is bad software, malicious software. It's software that's designed to wreak havoc on our system. So it'd be like a computer virus. A virus comes into your computer and it affects it and it spreads it like a worm. It spreads it to other computers on the same network. A Trojan horse is a software that looks like it's legitimate and not bad. But when you open that software, it actually is something like a virus that's going to try to go in and infect other files. So let's see, I'm really dating myself here. What was the Ali McGraw, the program from the 90s, and she had the dancing baby thing, the dancing baby meme where the baby dances. So there was a Trojan horse where people put up, oh, download this file. It's a cute video of a dancing baby. And while the baby is dancing, it's formatting your hard disk drive and encrypting all your data in the background. That's a Trojan horse. Okay, reconnaissance attacks are the things that, if I'm going to attack your network, I need to do some reconnaissance first. I need to map out all your IP addresses, all your port numbers, all your servers. And then I need to try to actually break in and get access. And the idea here is I'm going to do some denial of service. I'm going to encrypt all your data so your people can't do any work anymore and charge you a ransom to get it back. So people in the outside world that are not good people can use things like NSLookup and Whois to find what IP address has been allocated to the junior college, for example. And then I can try to ping all of those publicly available IP addresses to see which addresses are active. So as network managers, we try to do things that's one of the reasons why you can't just ping everybody in the world. The companies have disabled the ping because that's the way the bad guys come in and map out your network to try to attack it first. How can I access your network? Well, we're password protected, ain't we? Well, what about if I use a password attack? I'll use a packet sniffer and I'll learn your password. Or I'll just try every possible password in the world until I get your password. Because computers have got pretty fast these days, they can try every possible password in shorter amounts of time. Maybe a trust exploitation attack, where I'm going to use some privileges to get access to some device. A port redirection attack. I'm going to use secure shell, which uses port 22, to connect to a compromised machine that I've broken into, and then I'm going to metastasize myself like a cancer to port B, which was okay, but now I can access it. The man-in-the-middle attack, I sometimes call this the monkey-in-the-middle attack, is I go between two legitimate host machines, and I'm going to read or modify the data that passes between them. So if I log into the evil Chase Empire Bank to check my balance, the man-in-the-middle attack is intercepting the data he passed on to the real Chase server, my name and password, which he somehow got a hold of. And then he's receiving everything that's coming back. And then when I go the next day, he's cleaned out my bank account. A denial of service attack is where I want to stop you from being your people, authorized people, or customers or employees from using the servers. So have I used a term in here? You know, activist, a political activist has some particular aim or agenda. A hacktivist is an activist that can hack the network. And maybe some activist has decided that he doesn't want Bezos, Jeff Bezos, I call him Bezos the Beast, he's the head of Amazon. Bezos is making too much of a profit here. So we need to crash all the servers so we won't make so much money today. So I'm going to do some distributed denial of service attack on Prime Day and try to keep him from selling all his products. So I'm going to zombify 10,000 ISP people that I've taken over their home machines and use them to crash their server with 10,000 simultaneous requests. What can we do as network managers and technicians and engineers to fix these problems? So we can use things like firewalls. And a firewall can be programmed to only allow in the type of protocols that I've decided are to be allowed on my network, and only allow out stuff that should be not get to the outside world. A virtual private network is a scheme if we're using a public internet connection as the way in and out of our company, and we want to talk to a branch office. Well, we don't want everybody in the world to see that. With Wireshark, we can encrypt it and use a virtual private network so that only authorized people can see this. An intrusion protection system is this thing we put inside our company that looks for stuff that's bad. So you can get an open source intrusion protection system like Snort the pig, and it'll look for, you load a template file onto it, it'll look for stuff that shouldn't exist on your network, and if it finds it, it'll send you an email message or a text or something of that nature. Our one best defense against anything that could happen, hard drive crashes or ransomware occurs or something happens, there's a flood in the data center, and let's see, what's the most important file on our company servers that we simply cannot afford to lose under any circumstances? The accounts receivable file of who owes us money. If we lose that, we're stuck, we're out of business. So we need to back up everything on the network. We would back up to tapes. These days, hard disk drives are cheaper than tapes, so we just back up to other hard disk drives. And backups can be performed. There's a lot of data on most company networks. So maybe we'll do a full backup on the weekend, and then we'll do partial backups of change files during the week. Regardless, when you back up, you should test your backups to make sure that they work. Do a test restore and make sure it works properly. And where should we put our backup tapes or backup drives? Not in the same room with the servers. What if the server burns up or gets a flood? So for example, when I was at Harcourt in the 90s, I would back up to tape, and then we'd take the tapes down. I would take the tapes down to across the street from our office building, there was a bank, and I would put it in a safety deposit box in the bank. So if our room burned up, we would still have backups. Backups should be protected using passwords so that if anybody gets hold of an old tape, they can't see your company data. Another thing we should do is, Windows is pretty good about this. Even Mac OS X and Linux distributions are pretty good about keeping the software updated. So if Microsoft finds a vulnerability, they'll issue a patch for it. And most Microsoft machines out of the box, if you don't change them, otherwise they'll automatically update themselves. So we want to make sure that all the latest operating system files are up to date and have all the latest security fixes in them, so you're less liable to be broken into. Now, we talked about Radius in the last chapter. Authentication, authorization, and accounting. A AAA server is the thing that will check, what is authentication? Who are you? Well, prove it. Type the right password in. So I'm going to authenticate you on the network by you putting the proper name and password. Then after that, I'm going to authorize you to do a certain function. For example, you log into your bank, a credit card, how much money, well, your credit limit is $1,500. You can't make a $1,600 charge. And accounting is, well, what are those charges that you did on that particular credit card? A firewall is a device that sits between an outside, unprotected, untrusted network and my inside network that I have full control over. I don't have any control over the rest of the world, but I can control what's in my company premises. So the firewall will prohibit certain types of protocols or data to come in from the outside world to my inside network, like maybe a ping request. I don't want ping requests coming into my company because they're going to use that to surveil my company and try to figure out what to break into next. Some companies will place their public web server and mail server in something called the DMZ. This is a special subnetwork within my company that I expect to get attacked because it's my public web server. I'm going to make that server especially rugged. We call these a Bastion server. Very rugged, not running any protocols that aren't being used, just running the web server process, for example. And then my inside protected network is in a separate network that can't be attacked by outside users. So it's a sort of a three-tier type philosophy. So some firewalls just look at the packets and they filter it based upon IP or MAC addresses. In the later part of the fall, we'll have access control lists with Cisco devices where we can allow this IP address but not allow that IP address. We can also filter based on applications. Well, web applications support 80, mail applications support 25. So maybe we can allow incoming email and allow incoming web requests, but don't allow incoming telnet or ping requests, for example. URL filtering is you're going to get to go to Yahoo and Microsoft Network, but you shouldn't be able to go to, oh, let's say this, the Pirate Bay. Many companies filter access to the Pirate Bay because its typical use is to get software for free, and the companies don't want the legal burden of this. And stateful packet inspection is we can actually open up the packet and check it out to make sure that unless it's permitted specifically, it's going to be denied. Now, the usual trend in security many years ago was allow all traffic except that which is specifically denied, but the new philosophy is let's deny all traffic except that which is specifically authorized or allowed. Endpoint security is something that runs on your desktop PC. So you're running Windows on your laptop or desktop PC, and Windows has some security code in it that does a pretty good job of checking for malware or viruses and things of that nature. So Tarrant County College has got a certain endpoint security, and we use a Cisco-based endpoint security that we place on our machines to check for things like viruses. Now, when it comes to device security, the default values are usually inadequate. So there is a command that we don't have to actually configure this anymore. We used to have a lab for this, but it's no longer required. You can run on a Cisco device, you can run an all secure command, and it'll lock down the system. It'll make passwords be changed, it'll restrict access, and it'll put all the latest patches on that device so it has higher security than just out-of-the-box security. Now, there's been some argument about this, about passwords. Oh, the password should be 129 characters and impossible to guess. And actually, it's shown that the longer the password is and more difficult it is to remember, research has shown people will write them down in a yellow sticky note and put them underneath their keyboard. And the janitors know this, so the janitors log into your machine and use it at night. But these are the rules for the accepted rules for what we've talked about for years. Make passwords complex, a mix of uppercase and lowercase characters. Don't use a dictionary word. Change passwords often. Don't write them down and put them on a sticky note and put them underneath your desk or something like this. Now, on Cisco routers, leading spaces are ignored. So if you type enable secret space, 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 class, it ignores the spaces. However, I don't know what they're teaching you guys in typing class, but it seems like everybody, I watch people and they type enable secret class space, and then they put the enter key in. Whoa, well, what's the password now? It's not class, it's class space, enter, and you're locked out of your device because you think it's just class. For additional password security on Cisco devices, we use service password encryption, which hides those passwords that are normally typed and shown in plain text form. And we can set a minimum length of passwords if we want to. And we can also, if someone tries to do brute password forcing, try every possible password it could be, we can block it after 3 attempts. We're going to block it out for 30 minutes. And if you leave a terminal connected and you go to lunch, by default, you will be logged off of that device after about 5 minutes. So the exact timeout can be set to whatever value you want to, so that if you run away from a terminal for lunch, someone else can't walk up to the terminal and you're already logged in with your enabled secret password and they can mess with your device. We use Telnet in our Cisco labs, Network Academy labs, we use Telnet normally to go into a device like a router or a switch from a remote device like a PCA, PCB. But Telnet is unencrypted and everything, including the password, is in plain text form, and I can limit it with Wireshark. So if you want to secure a device, you can use the encrypted version of Telnet, which is Secure Shell, and it will use a public-private key pair to encrypt not just the name and the password, but everything on that particular device. And that way we can, if I have a device at a remote location, I have to go over the internet to connect to it. That way I can encrypt the data and it's safe and no one will be able to get in there and mess with it. And I think the last thing here is disable services that are not used. Remember that Bastion server I put in my demilitarized zone, my DMZ? I'm going to turn off all the services on that I don't need. I'm just going to have the bare web server code and the bare mail server code, and I'm going to turn off all the other protocols. Okay, let's see now. Is there, oh yes, there's one more chapter. Hold on. There's our chapter on building a network. Click, share. And let's look at devices in a small network. So is this even good English here? The majority of businesses are small. Most of the business networks are also small. Needs a comma there or something. Small network designs are usually fairly simple. They're usually going to have a single wide area network connection back to the home office or back to an internet service provider. Think of your home router network. If it's a large company, we're going to have an IT department to standardize everything and manage all of this. If a small company, you either do it by yourself or you'll use a managed service provider, MSP, to do that stuff for you. So when we choose devices for a small network, the considerations are going to be cost. And if you're unlucky to work enough at a company where the IT department reports to the chief financial officer, chief financial officers are very good with math, but they look upon all expenses as something to be reduced. And so they're not going to want to buy something that's expensive that will do the job and give better security. You're better off if you work at a company where the IT department reports to the chief executive officer, where the chief IT officer, the chief information officer, is a peer with the chief financial officer, and they can come together to the chief executive officer and the board and explain how IT brings value to the enterprise. It's not an expense, it's actually increasing our profits and revenues. And that way they'll agree, oh yeah, you do need a more expensive switch. We're gonna, these old switches have poor security and they need to be replaced. We also need to decide how many ports we need on our routers and switches. Can they be expandable? And what operating system features and services or feature set do we need to use on the software that's going to be used on those devices? In a small network, we're going to come up with an IP addressing scheme. And on most home networks, it's 192.168.1. something, for example. And we can use private addressing on our corporations too as well. Example, Tarrant County College uses the 10. network for our wired Ethernet devices and uses the 172.16 network for our Wi-Fi devices. When we decide what IP address range to use, we're going to need to know, well, how many devices do we have? All of our end user devices, like our desktop PCs, Wi-Fi devices, all our servers, printers, switches, routers, access points, all need IP addresses. So we need to determine the total number of IP addresses we need. And if it's less than 250, well, we can use something like 192.168. If it's thousands, we might need to use 172.16 like a Class B private inside address. But regardless, we're going to standardize on some address scheme and use that. Now, redundancy means, think about RAID drive arrays. I'm going to build a server and I'll put a RAID 5 array in it. And if any of the drive fails, we don't lose any of our company data, like our accounts receivable file. I could have redundant servers. I could have redundant switches and routers, and this triangle style connection so that there's, if any one element fails, any one router, any one wiring segment, any one switch, any one server fails, we should be able to continue company operations, maybe at a slightly reduced performance level, but we still push you over. I can't pay my people to sit there and drink coffee because the switch is down. Now, quality of service, traffic management. Some traffic needs to go to the head of the line. It's very latency sensitive. A voice over IP telephone call on a Cisco telephone set is very latency sensitive. It doesn't need a lot of bandwidth, but it does need very little delay. Any type of streaming audio or streaming video needs relatively small amounts of delay or it's going to mess it up. So we can have queues of priority and always go, maybe the voice is the highest priority and the FTP file transfer is the lowest priority. Common applications in networking. There are two common applications. Network applications are application layer protocols like Hypertext Transfer Protocol, Transmission Control Protocol. For applications that are not network aware, then the application layer services will accept that data and begin to prepare it to be transmitted upon the network. So common protocols include remote access, like Telnet and Secure Shell. Telnet's unencrypted. Be careful. If it's a sandbox on a Cisco network, kind of be lab, it doesn't matter. If it's in a production network, we probably would want to use Secure Shell. Hypertext Transfer Protocol and Hypertext Transfer Protocol secure HTTPS, it should say there, are used between web clients and web servers. Simple mail transfer protocol and POP3 and IMAP to pick it up. To send email, all of these days, you're probably using Google Mail or managed Outlook for your company to do this, and you're going to use simple web traffic for this. File transfer protocol, FTP. File transfer protocol is like Telnet, it's totally unencrypted, but there's a secure file transfer protocol that you can use if you want to transfer files securely. And our IP addressing services, Dhcp and DNS, will assign IP addresses dynamically to all our employees' machines and allow them to look up where they can just type in Cisco. They don't have to type in 128 binary values. No one's going to put up with that. Now look at this last point here. A single server in a smaller company, you might have one physical file server like running Microsoft Server 2019. And it might be the web server. It might be the FTP and web server. It might be the mail server. It might be secure self-server for the whole company on one device. Or maybe you're running virtualization on that one device and you have lots of different servers running on one physical box. So network protocols, there are tool sets. So they're going to do the processes, define the messages and the syntax. And many companies have a policy of only using the secure versions. Only use Secure Shell, not Telnet. Only use secure FTP, not regular unencrypted FTP. Use Hypertext Transfer Protocol secure, not unencrypted Hypertext Transfer Protocol. Warning, Will Robinson, if you come to a Tarrant County College location and use your Wi-Fi device that's your personally owned device, we do not encrypt that traffic. Anybody else could run Wireshark and see that information. Now, voice and video applications. This is where we're probably going to have to use TCP. We're going to use UDP because we want fast and low latency. Does our network have the capability of supporting all this stuff? Real-time applications, typically used for telephones and IP telephony and voice over IP? Do we have the capability of supporting all this stuff? We're going to have to buy some specialized controllers for our telephone, Cisco telephones, to support the dialing maps and the connection and give them the proper telephone number. Now, scaling refers to the process of taking a small network and growing it up to a larger network. So a couple years ago, we built a new air conditioning building on the end of campus, and we had to run fiber optic cable to that and put switches into that building to connect everything together with. To do this, we need to have some documentation of our existing network, physically and logically how it hooks up. We need an inventory of the devices. We need a budget from downtown to buy all this stuff. Well, thank you, taxpayers of Tarrant County. You gave us $800 million about a year and a half ago, so we can just buy anything we want to now. And we should also perform a traffic analysis on our network to see, how burdened are they right now with the traffic, and do we need to upgrade our traffic handling capability in the future. Protocol analysis is the process of looking at our traffic flow and seeing what protocols are being used. And we should do this maybe for a week, from Monday morning when everyone gets and logs in the network and is really busy and starting to do work, to the Friday afternoon at 4 p.m. where they say, I better get this work done. We're about ready to go home for the week. So we're going to analyze our traffic flow over a whole week, and maybe on a period like the last business day of the month to see when our peak activities are. And you can use a protocol analyzer, or you can use even Wireshark for free to look at this stuff and see how the traffic, or Cisco's net flow, which is not a CCNA topic, it's a CCNP topic. Now the employees will have operating systems that may have Windows. Windows has got the Windows, you press Control, Shift, Escape at the same time. You get the process manager. You can see all the things that are running on that. How busy are the CPU cycles on a desktop PC? How much RAM does it have free? So we can use things like Process Manager on Windows machines to see how busy our desktop PCs are. Now let's do some verified connectivity. Our big tool for this is ping, and what I call ping on steroids, Traceroute. If you want to be able to make sure you have connectivity from one point to another point of the network, you can use the ping command. It's on every operating system. It's a quick check to make sure we have layer 3 network layer connectivity between any arbitrary source and destination machine. I'll go to the source machine and I'll type ping 10.1.1.10, which is this guy over here. And if I have network layer connectivity to the whole network, PCB will respond to the ping and I'll get an answer back, and I'll know I have good network layer connectivity. Ping uses something called Internet Control Message Protocol, echo request and echo reply. There are some other things in ICMP, but that's all we're interested in for purposes of ping, to make sure that a destination, the host machines and source machines have reachability, have IP connectivity, network layer connectivity with each other. Now on Cisco devices, when you get answer, the exclamation point, that's good. That means it was successful. The period is, oh, that's bad, no connectivity. The U is bad, destination unreachable. There's a feature in Cisco devices called extended ping. I can, instead of typing ping 10.1.1.0, press an enter key, I can type ping and press enter, and then do a really extended ping and do some very sophisticated stuff, like instead of just a real short ping request, I can maybe stress test and use 65,000 byte packets. Maybe we want to do IP version 6 ping. We can use this for that as well. Now, I call Traceroute ping on steroids. Ping only tells us whether they have connectivity as a whole between two devices. What if there's a problem here or here or here? Where is the problem? I don't know. Ping just fails. Traceroute will tell me, was it at router 1, was it at router 2, or was it at router 3? Traceroute finds out the intermediate routers, what their IP addresses are, and using time to live magic will determine all these intermediate routers, and where the failure occurs, say there's a telephone line that went down between router 3 and router 2. I can determine that with Traceroute. I'll get to R1, I'll get to R2, but R3 won't work. So I can type trace on a Windows machine, you type trace RT, And in this case, it got to the first router, but it couldn't get to router 2, 3, or 4. So there's a problem between the first router and the second router. If I can't get the second router, I can't get the third one or fourth one either. On Cisco devices, I'm going to type the whole word Traceroute. And this tells me, oh, I've got to router 1, I got to router 2, I got to router 3 fine. And the left trace, I have a successful trace route, everything worked okay. On the right, I got to router 1 and 2, but between router 2 and 3, there was some problem, and I get the asterisk, which means no connectivity. So we have lost, there's a problem between router 2 and router 3. If it's our routers, then we can fix them. If it's our ISP's routers, we can complain to our ISP. Extended traceroute is like extended ping. We can do some extra options in here. In the Cisco iOS, we can type traceroute and press enter, and then specify the source and destination addresses and port numbers and things of that nature to try to do a more sophisticated test if ping failed. Okay, the network baseline, I mentioned this a little bit earlier. We should do a baseline for a week, because if something goes wrong and we've never measured anything, we don't know what the number should be. What are our metrics? So if we do a baseline measurement when things are working okay, then when something goes wrong later on, I can come back and say, well, it looks like the disk drive channel is okay, it looks like the CPU is okay, it looks like the memory is okay, but I can see something that's changed. I can narrow down the scope of the problem to one particular area and try to fix it. So you can copy and paste results from pings or trace routes to a text file, or you can get sophisticated network management tools like HP OpenView that will store in there and store this for you. But you can do it entirely for free. You don't have to buy a $10,000 network management program to do this. Now, on a Windows host machine, we can go to a Windows Network Sharing Center and quickly look at our 4 most important numbers: the IP address, the subnet mask, the default gateway or router, and the DNS value. Now, if it's a Dhcp environment, you can't see those from the network control panel, but you can go to the prompt and type ipconfig, and that'll show you the values that he's accepted there for this. For example, in our VMware virtual machines, sometimes they don't accept the value and you get zeros or you get no line there, and you got to disable or re-enable the virtual port to fix it. If you want to get rid of or check your DNS, you can type ipconfig/display DNS, and that'll show you all the entries. And I think there's one lab we do in the fall where you clear the DNS cache. Now on Unix machines, Mac OS machines, the command prompt, instead of ipconfig, it's ifconfig. And you can type this command, it'll show you similar information. What's the IP address, what's the subnet mask. And depending on what version of Linux you're using, it may look different. Some of the newer machines, the ifconfig command has been deprecated, and you might have to type IP space ADDR, short for IP address, and that'll give you the similar information. So on a Mac OS machine, we can type network setup, and it'll show us more information. Arp command, Arp is this feature that synchronizes a certain destination workstation's layer 2 MAC address with this layer 3 IP address. I know my MAC address. I know my own IP address. I know the destination machine's IP address, but I need his physical MAC address to create an Ethernet frame and send it to him, because I need to track the attention of that burn-in address on his NIC card, so I'll pick it up and bring it up to that device. So if I type ARP-A on my computer, it'll show me all the IP address and MAC address bindings of all the other computers I've talked with recently in the past 3 to 5 minutes. If I want to ping it, that'll make sure there's an entry there. Now there's a weird command here, net shell interface IP delete Arp Cache. But there's another command in Arp. You can type Arp --, and there's a variant of the command that'll clear the Arp Cache, or just wait 5 minutes and it'll be vanished. So common show commands that we can use to check out a device and gain some baseline information from it: show the running configuration, show me the interfaces, Show IP interface to see layer 3 network layer information of interface. Show ARP is like on the Cisco devices like ARP-8 on a Windows machine. It'll show me all the recent mappings. Show IP route will show the router's route table information. Show protocols will show me which protocols are running. And then show version will show me, oh, what's the serial number of the device, what interfaces it has installed, what version of the code is it running. Okay, my favorite command, show CDP neighbor. Every time I start a lab, I like to first of all wire the labs together, wire the routers and switches together, and on all the router ports, do a no shutdown. Don't have to do on the switches. And then do a show CDP neighbor, give them host names, like S1 for the switch and R1 for the router. And then type show CDP neighbors to see if they're plugged together properly. Because with show CDP neighbors, I can say that my gigabit 001 port on my router is connected to the fast Ethernet port 05 of the switch. Oh, and that's the proper wiring for the lab. That way you don't spend an hour doing a lab and you figure out, no, you wired it up improperly. And it's not going to work the way it's supposed to be. Show up an IP interface brief is in every lab that we do. Very quick way to check to make sure that the interface has the particular IP addresses proper and you didn't fat finger it. You didn't type 192.168, you type 129.168. And due to something called cognitive dissonance, if you actually type 129 instead of 192, you will literally LSD like hallucinate yourself into not seeing the 129. Your eye will see 192. Whereas you have a lab partner come over and take a look and say, hey, buddy, you fat fingered it, it's 129. Okay, troubleshooting methodologies. The 6-step troubleshooting technique is to identify the problem. We may ask the user about what problem. I can't log in, or my screen is scrambled. And then, based upon your experience, you're going to establish a theory about what you think the problem is. There may be more than one possible cause. Then you're going to test your theory, maybe typing some show commands or performing some fixes to see if that solves the problem. Then we'll go to step 4, implement a solution. Step 5, verify that it actually fixes the problem and document it. Now, very important, if you implement a solution in step 4 and it fails to fix the problem, immediately reverse what you did back to normal. Or otherwise, you'll do 10 different things and you have 10 different potential fixes in there, and now the thing is really hammered, it's really broken down. So if it doesn't fix a problem, immediately roll back to the state it was before and try another solution that may or may not work. Now, should I try to resolve the problem myself, or should I escalate it? If I don't have a lot of experience, I may resolve it to a more experienced employee at my location, or maybe to a managed service provider, or maybe contact the support desk for the company. If I have a problem, for example, with my Cisco router, and it's affecting, it's brought a halt to business operations, well, I'm immediately going to have a service contract with Cisco, SmartNet. I'm going to call Cisco and escalate the problem to them, and they'll be able to fix the problem for me quickly because they've seen every possible problem that could possibly ever be in the entire world. There is a debug command, which we have not used yet, but we will soon. The debug command in the Cisco iOS allows you to sort of peek under the hood at the code that's running and see what's going on. I'm going to type debug IP ICMP, and I'm going to check for ping traffic, for example. Now, the debug command is very selfish. It snatches all the CPU cycles. It slows down all the extra careful code lines that Cisco engineers, software engineers have put in their Cisco products to make them fast and efficient. So when you use debug, be cautious. It could put a large amount of information on the screen. The router could get so busy displaying debug that it starts dropping packets. So the rough rule of thumb is turn on debug in a limited instance as possible, just to check what you need to find out, and then turn it off again with the no debug all or undebug all. Debug is not shown on a Telnet session. It's only shown on the console port. So if I come into a Telnet or secure shell connection, I won't see my debug messages. I have to type terminal monitor to turn it on, and the terminal no monitor if I want to turn it off. By default, it is shown on the default console terminal that you normally plug into with that baby blue rollover cable. Okay, here's some troubleshooting examples. Duplex Operation. There used to be, they've fairly solved this problem recently, but there used to be 15 years ago, we would plug two switches into each other, and one switch would configure itself with a full duplex mode, and the other switch would configure itself in the half duplex mode, and we have a duplex mismatch. And one machine, the full duplex machine, thinks it can send and receive at the same time. The half duplex machine thinks it's a hub, and he can only send or receive, but not both at the same time. So we get a lot of errors. We have to fix this by actually logging into the particular device and forcing them both switches to be either both half duplex or both full duplex. Hard to find because we still get some communication, but we're getting a lot of errors and it's slow. Now on iOS devices, you manually type in an error, like for example, you type 129.168 instead of 192.168, and you have your cognitive dissonance in your brain and you just don't see it. So show IP interface or show IP interface brief, we can check these addresses, and if you're working with a lab partner, your lab partner maybe knows something that you just didn't notice. So you become blind to it because you typed it in and you don't see it anymore. On IP in devices, normally we're going to use DHCP. We're going to use DHCP everywhere now, except on static devices like routers and switches and printers and servers. So if a desktop machine normally is going to send out the DHCP discover my DHCP server and get me an IP address. If he cannot contact the DHCP server for some reason, he'll use something called automatic private IP addressing, and use a Class B address that Microsoft donated for this purpose, 169.254, and he'll make up an address in that range. So that way, if we have 5 devices in a conference room and they can't talk to the DHCP server, they will all be able to talk to each other. And the 5 accountants that are doing the working in the conference room, doing the analysis of the company budget lines, still be able to talk to each other. You can type ipconfig on your Windows workstation. If you see 169.254, that means it was a DHCP configured device, but he didn't get this answer back for some reason. So that gives you more clues as to what's going on. Now, I call the default gateway, routers used to be called gateways. Switches used to be called bridges. I call it the friendly neighborhood router. That's your home router that connects you to the cable company. In the business, that's the router that connects you back to your ISP or back to the home office. That gives you the access to all different networks. If that device goes bad, you can still ping the other student machines in the classroom. You just can't go away from that room. If the default gateway is not proper, or if it's an incorrect value, you won't be able to talk to devices in remote networks. So you can type ipconfig to make sure it's proper. On a router, you can type show IP route to make sure the routing table is proper. A router is typically going to be the default gateway for all those devices that are present on that particular network. And lastly, DNS errors. DNS is normally automatically assigned by the DHCP function, but you can use any DNS server you want to. He mentions OpenDNS here, which are hard to remember numbers. May I suggest Google's 8.8.8.8, which is their OpenDNS server, or the Quad 9 project, which I like to use, 9.9.9.9, which is good about filtering malware and stuff of that nature. Now, here's a Gonzo secret insider tip of the day. While I'm in a DHCP environment, I have to click the button that says I pin the IP address automatically, and I'll have to take their DNS value. Well, no. You can go to Microsoft Computer and go to the network control panel, and you can click the upper radio box that says obtain the IP address and subnet mask and default gateway address, but then you can click another radio box in the bottom of that box, and you can specify your own 8.8.8.8 or 9.9.9.9 or whatever value you want to use there, in case you don't like your cable companies. Some of the cable companies have been known to jack around with the DNS servers, and if you mistype Microsoft, they send you to a targeted advertising website. So you can choose your own with Microsoft computers. Okay, I think that is it for today, and I'm going to go on mute and hang loose in case there's any chat problems, and then I'm going to sign off for the day.